What if I told you there's a technology that handles billions of real-time events, powering everything from banking transactions to ride-sharing apps? That's Apache Kafka, the backbone of modern event streaming. In this crash course, you'll learn how Kafka really works. What are brokers, topics, and partitions? How does Kafka manage real-time data at scale? And how can you set up a Kafka cluster and publish your first stream? We won't just talk theory, you'll get hands-on with free labs, so by the end, you're not just watching, you're building. Let's dive into the world of event streaming with Kafka and see why it's one of the most in-demand skills in tech right now.
We'll start with a very simple example. Let us say that you're watching a news on your TV. What is happening here? A particular event is getting sent for you over a network so that you can watch it. Now, how would I define this event? I would define the event as a record of an occurrence or happening, often represented as a key value pair when it comes to Kafka. Now, when you are trying to stream something on your TV, may it be Netflix, may it be a news, you would not be getting one single packet, right? You would be getting a lot of such packets continuously over a network. Now, this can be called as an event streaming or a streaming service or a platform. So how would I define event streaming? Event streaming is the continuous flow and processing of event data in real time, enabling immediate analysis or a reaction. We will try to move to another example to understand this concept much better. Let us say that you're trying to book a taxi. What would you do? You would open the app, then try to put the location where you want to go, and then you book the taxi. What happens now is a broadcast event has been sent to all the nearby taxis asking if they want to accept a particular ride. Now, let us say that one of the taxi accepts your ride, then you get a notification saying that, hey, look, you have this taxi that has accepted your ride, and this taxi is, let's say, 5 minutes away, and it will be coming to pick you up in 5 minutes. So there are two events that are fired. One is the event that sent out the booking request, and the other event was the event that gave you the confirmation of the booking of the taxi. Well, what happens next? You take the taxi, you go through the city or the route that you need to, and then eventually you are going to reach the place or your destination. And when you do so, your trip is ended. Now, this whole flow, if I have to go through it again, so what were the events that were actually collected or sent in the app for different services? So the first one is the customer booking the taxi. This is event number 1. Then the driver accepting the booking so that the customer information can be shown to the particular driver, and the customer receives this information also that which taxi is coming to pick them up. This is event number 2. The event number 3 is taxi driver that arrives at the pickup point and they start the ride. It gives the confirmation to our service to bill you appropriately. Then what happens is there are two events, that is event 4 and event 5, that focuses on collecting the metadata of the journey itself. Which route did the taxi take? How was the traffic congestion, if there was any? So these are nothing but IoT related information. Was the taxi going at a very high speed, very low speed, etc.? This could be the telemetry data that the app would be collecting. And finally, we have event number 6. That is when the customer arrives at the destination and the trip ends. The moment this happens, a certain amount has to be deducted from the customer's wallet and the driver would be receiving this. During the same, the app would also take its commission. Now, all of these events play a very important role. It could be event 1, it could be event 2, or it could be event 6. Now, we have one question. What is a service that helps us to navigate or pass all of these events from one service to the other service? So, from the customer, let us say this is service number 1, an event has to be sent successfully to the application number 2, that is the driver app. If you think of this, we need a medium to make sure that the events are stored, then they are processed also at the same time. What is this medium that helps us to achieve it. I hope you were able to understand what is an event, what is an event streaming, and in real world where it is getting used. What is Apache Kafka? First, let us try to understand the definition of Apache Kafka. Apache Kafka is described as a distributed event streaming platform. This means it's designed to handle large-scale data in real time, making it perfect for building data pipelines and streaming applications. Whether you're processing events from websites, sensors, or mobile devices, Apache Kafka is a powerful tool to keep everything connected and flowing smoothly. Well, now that we have understood the definition of Apache Kafka, let us now look at how Apache Kafka fits into a bigger picture. So we have Apache Kafka, and then we have a lot of services that produce or write this data to Apache Kafka. Once the data is in Apache Kafka, we have other services that are able to consume this data from Apache Kafka. This diagram shows Kafka at the center acting as a hub for data movement. On one side, data comes in from various sources like web pages, microservices, IoT devices, and Android mobile apps. These are the producers generating the data that needs to be processed or stored. On the other side, Kafka sends the data to destinations like microservices, analytical platforms, and databases. This setup allows Kafka to handle real-time data stream efficiently, ensuring the information flow seamlessly between the system. Well, it's like a superhighway for data. But before we understand more about Kafka, we have to first understand why do we even need this centralized nervous system or a centralized backbone infrastructure to even consume and store all of this data or events coming from different services. What is the purpose of this? This takes us back to the event-driven architecture basics. Hence, let us try to understand this first. So, we have a system A. The system A can be anything. It can be a microservice, an IoT device, or any application that emits an event. Now, this event has to be processed by system B. Why does it have to be processed by system B? Because system B would need this information further to be processed and sent out or being stored, which system X is going to consume. Now, after system B consumes the event 1, it has to send out a message to system A that have consumed this message. And this is what we call as a processed event. Now, this is a cycle, as you can see. Now, imagine this at scale. We have system A that is emitting not one, but n number of events at a given point of time. Then we have system B, which has to process all of these n events at a given point of time without failing any of these events. Then system X is going to consume it. But the work doesn't stop here. System B also needs to send back the event response to system A. Now, all of this at scale is going to put so much load on our systems. We might have issues when processing these events, or we might have issues when sending back the processed events to system A. Well, this is exactly where Apache Kafka comes into picture. But before that, let us try to understand what are the pitfalls in an event-driven architecture. In an event-driven architecture, services can become so intervened that they start hindering the updates and flexibilities. When services are too dependent on each other, making changes or scaling them becomes a nightmare. Think of a major e-commerce platform like Amazon. If their order processing system is too tightly coupled with their payment system, updating one could break the other, causing delays or even outages during peak shopping seasons like Black Fridays. So, keeping these connections loose or modular is key to avoiding this pitfall. Next, we have got reduced scalability. Event-driven system can struggle to handle growing data and user demands, especially if there are too many interdependencies. Picture this. You are at a concert and the sound system can't keep up with the crowd's cheer. It starts cracking and failing. That's what happens when an event-driven system can't scale efficiently. A classic example is social media platforms like Twitter. Back in the day, they faced scalability issues during major events like Super Bowl when millions of tweets flooded at once. If the architecture wasn't designed to scale horizontally, the system would buckle under the pressure. Avoiding tight interdependencies and designing for growth is crucial here. Now let's talk about a single point of failure. If one service goes down in an event-driven system, the whole thing can crumble like dominoes. It's a scary thought, right? This is why redundancies and fault tolerance are so important. Think about a cloud-based service like Netflix. If their event-driven recommendation engine fails because of one critical component crashes, users might not get personalized suggestions, or worst, the streaming could stop. Well, that's a big deal for millions of viewers. Designing systems with backups and fail-safes can prevent this domino effect and keep everything running smoothly. And here is a big one. No message persistence. If events aren't stored or persisted over time, your risk of losing critical data and creating inconsistencies is higher. Imagine sending an important email, but it vanishes into thin air before it gets delivered. Well, in real world, financial systems often rely on event-driven architectures. For instance, a stock trading platform needs to ensure every trade event is recorded and persist, or you could end up with a lost transaction and major financial headaches. Adding persistence mechanism like message queues or databases can save the day and keep your data safe. Finally, we have to talk about the limited functionality. Without advanced features for reliable and efficient event handling, you might miss out a full potential of event-driven architecture. It's like driving a car without GPS or a turbo engine. You're getting there, but not as fast and as efficient as you should. Consider a logistic company like FedEx. Their tracking system relies on event-driven architecture to update package statuses in real time. If the system lacks advanced features like real-time analytics or error recovery, customers might lose critical update, leading to frustration. Investing in robust tools and features can unlock the true power of this architecture. And there you have it, the top pitfalls of event-driven architecture and how to stay clear from them. Well, now that we have understood this, let us go back to our architecture. So we have system A, which sends out an event, but this time it sends out an event to Kafka. The work of system A is done. Then we have system X and system B, who can independently consume this message from Kafka. System A doesn't need to be aware of where it is sending the data, in the sense if it is sending data to system B or system X. The work of system A just finishes the moment it sends out the data to Kafka successfully. Similar way, system X and system B doesn't need to be aware where the event is coming from for them to be processed. All they care is to make sure that the event they need is present in Kafka and it is coming. Once we get the event, system B can process it and mark it as a processed event. Well, now I hope you understand how Kafka is turned as a backbone for an event-driven architecture. Well, with this feature, how does it make a big difference? Let us try to understand that now. Well, Kafka brings in some incredible strengths to the table. Let's dive into its key features one by one and see why it's such a game changer. First up, the high throughput. Kafka is designed to handle massive event streams with ease, ensuring no messages gets left behind. Whether you are dealing with thousands or millions of events per second, Kafka keeps the data flowing smoothly and efficiently. Next, we have fault tolerance. Kafka distributed architecture guarantees resilience and high availability even with failures. If one part of the system goes down, Kafka ensures your data stays safe and your system keeps running. Now let's talk about scalability. Kafka enables instant data to effortlessly scale to meet growing demands without service disruption. As your system grows, Kafka grows with it, maintaining performance and keeping everything running seamlessly. Is the perfect solution for evolving needs. Finally, we have got real-time processing. Kafka's low latency stream processing enables instant data insights and actions. With Kafka, you can react to events as they happen, delivering up to the second response and keeping your system agile and responsive. And that wraps up our deep dive into Kafka's role as a backbone of event-driven architecture. It's pretty powerful, right? We are going to understand a real-world use case of how Apache Kafka is used in a financial world. And the use case that we are going to discuss now is about real-time transactional processing. Let us try to visualize this architectural flow now. So, we have different kinds of payments or transactions done on a financial service or a financial gateway. The first thing is the payment gateway. That is nothing but the credit card transactions or debit card transactions or UPI payments, QR code scans, anything. Then we have the online banking transactions that take place. Then we have the cash transaction that takes place through withdrawal of money from ATMs. Nonetheless, all of these are some kind of transaction and it has to be logged in real time. Well, one good part about this is every kind of transaction is also an event. So, when one of these takes place, what happens is all of this information flows to one particular topic. Let us consider this as a transaction topic. Now, what is a topic? We are going to discuss all of this in detail in the future videos, but one thing is certain. A topic is a place where all similar events related to a service can be stored. Now, what happens next once we have this data in this particular topic? We will consume this information. Now, why do we have to consume this? Because we want to see if this particular transaction is in compliance with our service. And then we have to see if this transaction is fraud related transaction. And finally, we also have to update the balance sheet of this particular account. Hence, all of this takes place inside Kafka. So, Kafka is again acting as a central nervous system where it is storing the events, or we can say it is storing the relevant events in what we call as a topic. So, all the transactions flows into the transaction topic. Then we consume all of this information, do some pre-processing, and finally, we update this information to the account update topic. The moment you have this updated in the account update topic, let us say that you get a notification that certain amount was either credited or debited from your account. Now, if this is some kind of fraudulent transactions or a transaction that is not under the compliance service that we hold in the bank, then you might get a notification that this amount is on hold. Now imagine how many transactions happens around our world. Either it could be from payment gateway, online banking, ATM, every second. Well, we don't know, but we know it's a huge number. And Kafka is at the center of all of this. Well, This is one use case related to how Kafka is getting used in a financial service. In this video, we are going to see how Kafka is working in an EV charging station. Well, an electric vehicle charging station is very common nowadays, right? But in the backbone of it, it does do a lot of things to make sure the owners of the electrical vehicle can charge their vehicles at the right time in the right place and be notified about the sale. Now, what do I mean by this? Let us try to understand that now. So, we have a charging station. Now, in this charging station, we would need to know how many charging stations are free so that we can take our electrical vehicle or EV vehicle there and get it charged. At the same time, when we charge our vehicle, we would like to know for how long did we charge our vehicle and get billed accordingly. So what happens here is we have two kinds of events. That is the status of the charging station itself, and then for charging stations that have been used, we would need to know for how long and bill the particular user accordingly. So again, these two are certain events. Now, if you observe carefully, these two are sent to two separate topics because they are separate events, right? Can they be sent to the same topic? Definitely they can be, but it doesn't need to be. We can separate this to make sure that the further processing can become easier. So, if there is a charging station which is used, then all of this information goes to the charging session topic. And then if there is a charging station that is free, then this information goes to station status topic. Now you might be wondering, well, how does this information flow? Well, this happens with IoT devices. Basically, we have sensors that are going to sense this change and are going to trigger such events and send it to Kafka. Now what happens after that? So let us say that somebody is using our EV charging station. So the moment they start charging, we get an event and we are going to start our counter. That is for how long have they been charging it. And finally, we also have the status of our charging station. Now imagine there is a charging station where there are 15 chargers. Now if I were to go and charge my vehicle there, I would like to know if there is any charging station free today or not. Or I might want to book a particular charging station, so when I arrive, it is free. Now, all of this I will know only when I am getting a real-time streaming update of the status of our charging machines. Like I said before, all of these events can be sent using Internet of Things or IoT devices that relies on sensors. Now, let us imagine that all the information related to the station status topic can be aggregated and we can send this to an app where a consumer can see it. Now next is somebody have used the charging station and they finish charging. Immediately we would want to send this information to another topic, that is charging payment system. So here there is an information that this particular vehicle used this charging machine for how many minutes or how many hours, and then we bill this particular user accordingly. Now, what happens to the station status report? It can be accessible by our users using an app to know which charging station is free. Nonetheless, it can also be used by the charging station administrators to also monitor the whole charging station itself. And the good part is they can do it remotely. Well, I hope you understand how Kafka again is acting as a backbone to hold all of these real-time events and make sure it can be consumed in real time and then also display all of this information in real time if required. As I mentioned, there is a lot of companies that have been using Kafka now, and it is a de facto tool as of today in any event-driven architecture design that gets made. In this demo, we are going to set up a Kafka cluster using Docker. Not just that, we are also going to set up a Kafka web UI so that we will be able to visualize our Kafka cluster. So let us now jump into our demo. So here I am using my code editor. This can be any editor of your choice. All you need is Docker installed. The first thing I want to do is to create a Docker network. Let me run this command in my terminal now. Well, the Docker network has been created. The next step, we are downloading a Kafka Docker image. So this is from this particular Docker image, and we are giving it a name. Not just that, we are also saying it to join to the particular network, that is the Kafka network, and here we are mentioning the network. We are also enabling some port forwardings required for our Kafka cluster. Now, what are these ports? We are going to understand this in detail in the later section. Well, let me copy this command now and run it, and then press enter. So it is not able to find the Docker image. So it is going to start pulling the Docker image from the Docker Hub. Well, if you are using any kind of other Docker repositories like AWS, etc., you can also pull this image from there, but you just need to make sure to change the name here. That's all. Well, let us now wait for this Docker image to be pulled and the container to start. This command was completed. So let me first clear my screen and then let us go ahead. The next step is to start a Kafka UI. Please note that in Apache Kafka itself, we don't have a Kafka UI. What I mean is, Kafka UI is not a part of the Apache project. So the Kafka UI that we are going to use is built by someone else. So in this case, it is from this particular company. Again, it is open source, so we are good to use. What we are doing here is the same. We are pulling a Kafka UI Docker image and then we are running it inside the network. And we are enabling a port. Now, because it is running in the same network where Kafka is running, the Kafka UI will be able to connect to our Kafka cluster easily when we configure it. Let us try to run this command now. Click on paste and run. Let us wait for this particular Docker image to be pulled and the container to be in the running state. Looks like the container is now running. So let me clear my screen and do Docker container ls. And we are seeing that we have both the containers up and running. So let us go to the ports and let us open this particular port, that is 7000. So it should open the Kafka UI. And there we go. We have our Kafka UI. Now this is the first screen that you're going to see because it is asking you to configure a Kafka cluster. So let us give a name for this Kafka cluster. We're going to say Kafka local cluster. And then we have to give a host. Well, what is the host name? Just give the Kafka cluster. So this is also the name that you give for our container. So let us give the name. And what is the port? We are able to connect to Kafka always on port 9092. This is one of the broker port. Now, what is a broker? We are going to understand this in our future videos. So once this is done, you can click on validate to make sure that the Kafka UI is able to connect to the Kafka cluster. And you should see a success message in the bottom. So let us click on validate again and you see a success message, which means that the Kafka UI is able to communicate with our Kafka cluster. Then I'm going to click on submit. That's it. So the connection details has been stored. Let me refresh the screen quickly and click on reload. Well, you see the Kafka cluster is now configured successfully. Now, if I want to see some information about my Kafka cluster, what can I do? So for that, let us click on brokers. Now here, we only have one Kafka cluster. So that is why you are seeing on the drop down on the left side. So this Kafka cluster is running on our local system. So it has only one broker. It has the version of Kafka and it has a number of partition mentioned and it has a disk usage utilization. Now, what is a broker? What is a topic? What is a consumer? We are going to dive deep into each of this in detail in the future section. Let us click on topics and by default, you're going to see a lot of topics. These are all the test topics that are created. Well, this is a way in which you're able to set up your Kafka cluster using Docker very quickly and practice Kafka hands-on. Well, the Kafka UI itself is not a must. But if you don't want to run a lot of Kafka commands in the CLI, the UI does come handy to quickly visualize your Kafka cluster itself. Well, that is how simple it is to set up Kafka locally. In this section, we are going to focus on understanding the key technologies or services in Kafka that are considered as building blocks of Kafka. To make this learning easy, let us first try to understand the use case. We are going back to our EV charging use case. So we have a Kafka cluster and then we have our producers. Producers are nothing but some of the services or IoT devices that produce events. Now, when these events are produced, they land in what we call as a topic. Now, what is a topic? We are going to definitely understand that in this particular section. Once this data lands in these topics, the other services will consume it and produce some kind of relatable results. We were able to understand this architecture in detail in one of our previous videos. Now, using this same use case, we are now going to understand some of the building blocks of Apache Kafka. The first one is Kafka brokers. So we want to understand one use case now, that is the station status report. So imagine you're trying to book an electronic vehicle charging station. Now what would you do? You would like to open an app or a UI to see how many of these stations are currently free and can you book something so that you can go and charge your vehicle at a given point of time or during the interval that you require. So this is the use case. So we have our producers, that is the EV charging stations and the charging stations itself. These produce the event, but where are those events actually stored? They are physically stored in what we call as brokers. Brokers are nothing but physical machines and they have hard disks attached to them. The messages or the events that flows through Kafka are actually stored on what we call as brokers, and in turn these store the information in the hard disk. So to summarize what is a broker, a Kafka broker stores and manages messages in a cluster. So this is the role of a Kafka broker, that is to store the events coming into Kafka and manage it properly. Now it is time for us to understand some of the characteristics of these Kafka brokers. The first one being the message management. Kafka brokers handles the storage and retrieval and distribution of messages efficiently. Every message flows through a broker, ensuring reliable data delivery across consumers. Without brokers, managing large-scale real-time data streams would be chaotic and unstructured. They act as a backbone of distributed messaging, ensuring seamless communication between producers and consumers. Next, we have the cluster node itself. As I mentioned, each Kafka broker acts as a node within the cluster. These nodes communicate with each other, maintaining a distributed system that supports large-scale data streaming. This distributed design helps prevent bottlenecks, ensuring smooth data flow across multiple applications. By distributing the workloads across multiple nodes or brokers, Kafka ensures reliability and performance at scale. Speaking about scalability, brokers enable seamless horizontal scaling. As data volume grows, additional brokers can be added to distribute messages across multiple nodes, ensuring optimal performance. This elasticity makes Kafka a powerful choice for organizations handling dynamic and growing data loads. Whether managing small-scale applications or enterprise-level data pipelines, Kafka scales effortlessly. Well, it means Kafka also needs to have a very good fault tolerance level, and definitely it has one. If a broker fails, redundant copies of messages ensure no data loss happens, maintaining durability and system reliability. This redundancy mechanism is crucial for businesses that depend on uninterrupted data streaming and processing. Even in cases of hardware failure, Kafka's architecture guarantees high availability and data integrity. Now you might be wondering, as the data scales, we might be having a lot of brokers or nodes, correct? So managing them would be difficult. Well, they are, but Kafka offers what we call as a dynamic membership. Kafka brokers can dynamically join or leave the cluster without downtime. This flexibility enables high availability and easy system maintenance. Organizations can effortlessly expand or optimize their Kafka infrastructure without disturbing the ongoing operations. This makes Kafka ideal for businesses that require continuous real-time data flow without service interruptions. Now that we have explored what Kafka broker is and how it is powerful in real-time data streaming, let's take a look at some of the biggest Kafka deployments in the world. Companies like Netflix, Pinterest, PayPal, and LinkedIn operate at an incredible scale, running thousands of brokers across massive clusters to handle trillions of messages every day. Netflix leads with around 4,000 brokers across 50 clusters, supporting a trillion messages daily to keep your streaming experience seamless. Pinterest matches that scale, pushing 4 trillion messages a day at 50 GB per second, storing an exabyte of data in AWS S3. Well, PayPal isn't far behind with 1,500 brokers over 85 clusters, ensuring 99.99% uptime for secure transactions across the globe. And of course, Kafka's birthplace, LinkedIn, runs with around 1,400 brokers to power 1.4 trillion messages every day, driving their data-driven ecosystem. Well, these numbers showcase the raw power of Kafka in action. Whether it's streaming, paying, or connecting people, these tech giants prove that Kafka scales like a champ. And one of the reasons for making that to happen is also the underlying fundamentals of Kafka, that is, Kafka brokers. In this video, we are going to focus on organizing this data that is coming into Kafka. So let us go back to our previous example. So Kafka brokers are responsible for holding all the events that are coming in from our producers. The next question that arises is, how do you categorize these events so that accessing them will become easier? Now, with the same example, we'll try to understand this. So let us focus on the station status consumer report. Now, if you want to get this information alone, we need to connect to one of the events coming from the producers, correct? Now, how do we know where this event is? For this, we have to make sure that when our producers are producing these events, they get produced and stored in a categorized manner. And this is what we call as a topic. As we can see from this example, the EV charging station is sending all the events to a topic called as EV_charging_topic. And charging station is sending all the events to a topic called as station_metrics_topic. Hence, topic is a logical way of organizing and categorizing the Kafka messages. That's it. So it is not a physical concept like broker. When we create a Kafka cluster, the first thing that we create is a bunch of brokers. And then what we create is a Kafka topic. These two form a building block for us to start sending the events to Kafka and also start consuming these events from Kafka. Now, just like Kafka brokers, you also have features for Kafka topics. Now, what are those features? We will try to understand that now. First up, let us talk about message categorization. Kafka topics are all about grouping related messages logically. Think of topics as containers that hold messages of a similar type, like emails, logs, or IoT sensor data coming from respective devices. You can create as many topics as you need to organize your data streams effectively. Kafka doesn't impose a hard limit on the number of topics you have, but there are practical limits based on your cluster resources. For example, each topic creates metadata overhead. So, if you have tens of thousands of topics, you might need to tweak settings on your brokers to handle the load efficiently. With messages neatly categorized, let us explore what makes Kafka topics so reliable for processing those messages in the right order. Moving on to the next feature, it is immutable logs. Everything in Kafka that gets stored is in the format of a log. In Kafka, messages within a topic are stored sequentially in an immutable log. Once a message is written to a topic, it cannot be changed. This sequential storage ensures that consumers can process messages in the exact order they were produced, which is critical for a use case like financial transaction or event sourcing. Here is an interesting fact. The immutability of Kafka logs is tied to its retention settings. You can configure how long messages are retained either by time, like 7 days, or by size, let's say 1 GB. But here is a tip. If you set retention too low, you might lose data before consumers can process it. So always align your retention settings with your application needs. Now that we know messages are stored sequentially, let us see how Kafka topics enable collaboration between different components of our system. Next, we have multi-consumer access. Kafka topics allow multiple consumers to read from the same topic without interfering with each other. This means you can have different applications like a fraud detection system and a reporting dashboard consuming the same data stream independently. Each consumer keeps track of its own position in the topic using offsets, ensuring smooth and decoupled access. Next up is about decoupled communication, which we just spoke about. Kafka topics enable producers and consumers to interact through topics, not directly with each other. Producers write the message to a topic and consumers read from the topic at their own pace. This decoupling is what makes Kafka so powerful for building scalable asynchronous system. You don't need to worry about synchronizing producers and consumers. They operate independently through the topic. Finally, we have the concept of replication. Kafka topics ensure data availability by replicating the messages across different brokers. Well, we will be understanding the concept of replication in much more details in the future video. And there you have it. 5 key aspects of Kafka topic that make them the backbone of your data stream. From categorization to replication, topics provide the structure and reliability you need for real-time data processing. Let us now use a UI to create a Kafka topic. So let me go back to my Kafka UI now. So here I am on my Kafka cluster. So here let us click on topics and click on add a topic and give a name for the topic. I'm going to say Kafka Lab. As you saw me typing, so the Kafka name needs to follow a certain format. So the moment I give a space here, it is giving me another. So let's say Kafka Lab here. Number of partition, we are going to say 1, and then the retention as 7 days. That's it. Well, what are this configuration? Why is it important? Again, we're going to dive deep into each of these configuration in more detail in future videos. For now, let us create a simple topic and click on create topic. And that's all. So we have our Kafka topic created. Now, can we create a Kafka topic also using a CLI? Definitely, we can. But this is where the UI comes handy. If you're practicing something, if you're developing something locally, setting up this Kafka UI is going to make things much easier. Well, that is how easy it is to create a Kafka topic using the Kafka UI. That is it for this video. Speak with you in the next video. Thank you. In this video, we are going to focus on how Kafka is able to achieve high availability by using 2 of its unique features, that is partitioning and replication. To understand this, first we will go back to our architecture design that we have been discussing. We have the charging station and we have our Kafka cluster. The charging stations sends out all of their information to a topic called as charging station status. Now here we have learned that this information is getting stored in broker 01. Now, a few questions arises. What happens if this broker goes down? What will we do if we have to scale the consumption of this particular information? Imagine all of the processes trying to rush to get this information from this topic on broker 1. Would it really survive? Not really. Broker 1 at some point of time would end up having a high CPU utilization or a RAM issue and would probably fail. Then how is Kafka handling this? It is doing so by partitioning this data into multiple brokers and separating it. Before we see how it does this and how the architecture would look like with partition, we will try to understand some basic information on why we need partitioning and how it actually helps us. The first one is the distribution. Kafka uses partitioning to distribute a topic's data across multiple brokers in the cluster. This means that if you have a topic, its data isn't stored on just one broker, it is spread out. This distribution ensures that no single broker becomes a bottleneck and hence maintain high availability even if a broker goes down. Now let's talk about the parallelism. Partitions enable parallel processing of messages by consumers. Each partition can be consumed independently, so multiple consumers can process messages at the same time. This parallelism increases throughput, making Kafka highly efficient for handling large-scale data streams. Moving on to the scalability. Partition allows topics to scale beyond the limit of a single broker. A single broker has finite resources like CPU, memory, and disk. But with partitions, Kafka can distribute the load across many brokers. This makes Kafka incredibly scalable as your data grows. Now let us speak about the fault tolerance. What happens if one broker fails? Partitions on the other brokers remain available, right? That is done using the concept of replication, and we shall understand this in a bit more detail in a few minutes. Finally, let us speak about ordering, and this is important. Within a partition, messages are strictly ordered, providing a clear sequence of events. Kafka guarantees that messages in a single partition are processed in an order they were produced, which is critical for applications that rely on event sequencing. Well, now that we have covered on the high level the benefits of the partitions in Kafka, let us zoom in on the specifics of partitions in Kafka. But before that, let us update our architectural diagram and see how it looks. So we have our Kafka cluster, we have our charging station. Then we have 3 brokers. We have a topic called as charging station topic. Did you already observe how we are mentioning or trying to visualize the topic? It is not on one broker. It is spread across different brokers. Then we have partition 01, partition 02, and partition 03 for this particular topic. So charging station topic has 3 partitions. You observe here something called as a key, that is station A and B. We'll understand what are these in the later stage, but for now these are called as message keys. So station A and station B start sending out the information and they get distributed across different partitions, as you can see. This is how partitions are utilized in Apache Kafka. Now let us dive into a bit more specific details. We start off with a partition key. When producing messages, you choose a partition key that eventually distributes messages across partitions. For example, if you are processing user events, you might use the user ID as the key. This ensures that the messages from the same user go to the same partitions, avoiding imbalance where one partition gets overwhelmed while the other sits idle. Overpartition can be an issue too. Excessive partitions can lead to overhead and management complexities. Each partitions require resources for replication, metadata, and coordination. Too many partitions can slow down the system and make it harder to manage. So balance is a key here, and you need to know how to partition a topic based on the use case. on the flip side, under partition is also an issue. Too few partitions can limit throughput, negating the benefit of partitioning itself. If you have too few partitions, consumers can't process messages in parallel efficiently, leading to bottlenecks. You need enough partitions to match your workload and consumer capacity. Moving to the data locality. Consider data locality to ensure related data resides within the same partition for efficient processing. If you have configured your partitions key properly, then data locality shouldn't be a big issue. Lastly, the consumer group size. The number of consumers in a group should ideally match the number of partitions for optimal consumption. Each partition is assigned to one consumer in a consumer group. If you have more partitions than consumers, some consumers will handle multiple partitions. If you have more consumers than partitions, some consumers will sit idle. Matching them ensures balanced and efficient processing. We are going to focus on another feature, that is replication. Let us go back to our example. We have different events coming from our charging station. The EV charging station itself, the charging station status, etc. We have two topics, EV charging station topic, station metric topic. Then we have some dashboards that are getting built on top of the station metric topic. Imagine that we lose broker 2. What happens? We lose the information of this topic completely. Now you might say, not really. We learned about partitioning just in the previous video. The data is actually spread across broker 1 and broker 2. You're right. The data is spread, but is it replicated? By doing partitioning in Kafka, you're not replicating it. You're just breaking the data and making sure that the data on a topic is spread across different brokers. But it is not replicated. And hence, we need to also know how Kafka works with replication enabled. And that's the other feature, that is replication in Apache Kafka. Now, if such scenario really happens and if you have no replication set, then we are going to have the status monitoring metrics down and the dashboards won't be refreshing, resulting in the downtime. So let us convert this to again the architectural diagram that we had. So we have station A, B, C and D, and we are going to focus on station A and B. Station A and B are sending data to the charging station topic. They have partition 1, 2 and 3. Now what happens if a particular partition actually goes down because of a broker issue? Let's imagine that partition 1 has an issue. How does Kafka really react? And if you have enabled replications in Kafka, how will Kafka handle this? We will understand this now. But before that, let us try to understand on a high level the reason why we have replications in Apache Kafka. We'll start with the high availability. In Kafka, if one broker fails, another replica takes over, ensuring continuous service. Replication ensures that there is always a backup of a copy of data, so the system remains operational even during failures. Next, about fault tolerance. Replications protects against data losses due to broker failures. By keeping multiple copies of the data across different brokers, Kafka ensures that your data is safe and accessible even if the broker goes down. Now let's speak about the scalability part. Replicas distribute the read load, allowing the system to handle more consumers. So remember, partitioning is already helping us with parallelism, and with replication, we are increasing the parallelism a lot more. With replicas, consumers can read from different brokers, reducing the load of any single broker and enabling Kafka to scale efficiently. Moving on to the data durability. Multiple copies of data ensure that the information is preserved even with failures. Kafka's replication mechanism guarantees that your data isn't lost, even if the broker crashes, making the system highly reliable. Finally, the increased throughput. As we said before, because of the replication, we are going to double the parallelism capacity with the addition of partition on a given topic. Cool. Let us now go back to our architectural diagram. So we have the charging station sending data to the topic, that is charging station topic. We have partition 01. Let us say that your replication factor is 3. What will happen is partition 1 is replicated to broker 2 and also to broker 3. Why? Because you have 3 replications set, correct? And if you had only 2 replications set, what would have happened? The replication would have happened either on broker 2 or 3, that's all. Because you have replication set to 3, the partition 1 is copied to broker 2 and broker 3. Now what happens? Now, in case broker 3 goes down and has an issue, then we lose one of the replicas. This is easy and it is fine because we will just create this again. That is not an issue. But let us say that partition 1 in broker 1 is the place where all the information is getting written and then it is getting replicated. Now what happens if that goes down? This is where the real problem starts. But in this case, what happens is the partition 01 on broker 2 will become the leader partition, and station A and station B are going to start sending the information to broker 2 itself. Why? Because broker 2 now has become the leader of this particular partition. Remember, partitioning and replications go hand in hand in most cases, and having them both enabled has a great value for Apache Kafka. In this demo, we are going to practice what are topics, partitions, and replications in Apache Kafka. Let us now jump into the lab section. We are in the KodeKloud lab where Kafka is already installed. To see all the binaries of Apache Kafka, you have to navigate to /root/Kafka directory. So let me make this screen a bit small and then let us list all the files here. There we go. Here is where we are going to find all the binary files of Apache Kafka. To run any CLI commands, we have to navigate to the bin directory. And here you are able to find a lot of shell scripts that we can use to communicate with Apache Kafka. Let us first now create a topic in Kafka. So let me clear my screen and then run the command. The command that we are going to run is kafka topic.sh. This is a bash script. Then we are sending some arguments, that is create, then topic, and the name of the topic, and then the bootstrap server. Now, what is the role of bootstrap server? This is how you will be able to communicate with Kafka. Because Kafka is running locally, we are using the localhost 9092. But in your organization, if the Kafka is running on a different environment, you will get the bootstrap server details from the Kafka admin or the SRE team that is maintaining Kafka, and you have to replace it here. Let us run this command now, and it is going to create a topic called as demo topic. It did give us a warning, but we can ignore it. Now, how do I know that this topic has been created or not? For this, we can use the web UI. So let us click on the web UI option here, and this opens the Kafka drop web UI. And here you are seeing the demo topic. So let me click on this, and you are seeing all the configuration details of this particular topic. Now, how can we create a Kafka topic with partitions involved? Now, partitions offers a distribution inside Kafka and also helps us in parallelization process in the later stages. To do so, let us go back to our lab section and run the command where we are going to specify the number of partitions that are required. So here we are running the same command again. So create topic, a new topic name, but then we are passing an argument called as partition, and the partition is 3. Well, the recommended way is to keep the number of partitions equal to the number of brokers. This is a best practice. In this demo though, we only have one broker, but it is fine for this demo, and I'm only showing this so that we can see all the properties of the topic. Then we are also mentioning the replication factor as 1. Then click on enter, and this should create a new topic. Again, to visualize this detail, we can go to the Kafka UI, go back to home, click on refresh, and you already see the new topic created. And if you observe carefully, we are seeing the partition details as 3. In the previous case, it was 1 because we didn't mention any and the default is 1. And then let us click on partition topic. Here you will find all the details related to this topic. If you observe the partition details, it is going to tell you the number of partitions we have, then the leader of this partition, which broker it is there, etc. If you want to check all of these details on the CLI, how can we do it? So for that, we can run the command kafka topic.sh, same bash script, but instead of create, we are going to mention describe. Then describe what? Describe a topic, the name of the topic, and the bootstrap server details. So if I press enter, it is going to give us all the details. Now this is the same detail that we saw on the UI. But in case if your organization doesn't have a web UI, you can use the CLI to get the metadata information related to these topics. The next thing that we want to understand is, how can I change the properties of a given topic? For example, in a topic, we have something called as retention days. How many days would you like to keep the information in this particular topic? Now, I already created a topic, but how can I change this information? Well, we can definitely do that using the CLI again. So now we are running a command called as Kafka config.sh, and we are saying connect to the bootstrap server. That is the details that is required for us to connect to the topic. Then entity type, that is a topic. So what is the config that you want to change? That is the topic. Then the name of the topic, partition topic. Then we are saying we are going to alter and add a config that is called as set retention.ms. So here we are setting the retention time in milliseconds. So let me click on enter and then wait. The details has been updated. So to verify it, let us go back to the UI and click on refresh here. And if you see, there is the configuration that has been added, that is retention.ms. To verify this on the CLI, we can run the same command again that we ran earlier to describe the topic, and you will be able to see the retention details here. And if you observe the previous output, you are not able to see anything. So if you see here in the config, we have segment.bytes and that's all. Now we have retention in milliseconds also. Now I mentioned that in this particular lab, we don't have that many brokers. How can I see number of brokers in this cluster? So if you want to do that, we can simply run this command where we are going to get all the details of the brokers. So the command was Kafka broker API version. So this bash script needs only one argument. That is the way to connect to Kafka. And then it is going to list all the details.